Welcome back. Today I'm talking about reserve design, which is a very important topic in spatial optimization and has a lot of analogy with some of the covering problems that we discussed earlier. I'm going to specifically focus here on the species set covering problem. The main issue we have at hand is the following. We have a few species and we would like to set aside a few parcels to maybe maximize the biodiversity, or maybe to guarantee that these species have an opportunity, or at least a place, rather, to survive, right? Now, there are a few assumptions that I think we should talk about first. In a given area, which typically is your study area, you must have a set of eligible parcels. Okay, if you don't have any parcels that can be set aside for preservation, then there is no point to even try to optimize anything, right? Each parcel contains a subset of species. So it's one thing to have a parcel, but if that parcel, let's say, is absolutely not suitable for biodiversity, then probably it's not even worthwhile to put that into the model. The species are designated as important, so we want to make sure that the species that we're trying to preserve are important from a biodiversity perspective. Now, some can be more important than others. There are different ways, we can define these species. And then the other assumption is that the species can survive in the parcel. So if they are spotted in this parcel, then they can survive. Of course, there are some parcels that are more suitable than others, and we can change those models accordingly. So the first thing, of course, I'd like to focus on is the species set covering problem. And before going into the formulation, let's try to understand what this model is about. We're trying to choose the least number of parcels. No, it could be the least number. It could also be the parcel that has the least amount of cost, such that each species is represented at least in one parcel. So each species here, I forgot to add this here, each species is represented in at least one parcel. Okay, so it doesn't matter if the species appear 2 times, 3 times, 4 times, because this is more of a backup problem. But here we're not focusing on that. So our objective to minimize the number of parcels. I like to take this example here, and hopefully this is clear. I have 3 different parcels. Okay, J equal 1, 2, and 3, and in each of these parcels I have spotted different species. A species A, species B in parcel number 1. In parcel number 2 I have B and C, okay? And in parcel number 3 I have C. So if the objective is to minimize the number of parcels so that each species is represented, you could have a combination of 2 parcels. You at least need 2 parcels here. You could have a combination of 1 and 2, right? Because then A, B, and C is represented. You could have 1 and 3 because then A, B, and C is represented, but you couldn't have 2 and 3 because if you have 2 and 3, then A is not represented, right? So we need to take that into account. Let's go and move into the formulation of the problem. Okay, I'm going to spend a little bit of time on the formulation of the SSCP. And what I'd like to first do is to define the different indices and the different sets. We have I here, which is the index of species, and capital I, which is the set of all the species. We have J here, which is the index, and then the set of all the parcels that we can consider to set aside. M sub I is a set of parcel J which contains species I, and which species I is likely to survive if that parcel is predicted or if that parcel is selected or set aside. So it's very similar to what we talked about earlier on the location set covering problem, where we had to identify which facilities could cover which demand node. Well, so here it's kind of just the way around. And then X sub J is a 0, 1, so that's a decision variable that is equal to 1 if the parcel J is selected for inclusion in the reserve set, and 0 otherwise. Now, what is the formulation looking like? And as I mentioned to you, it's very similar to the location set covering problem. We have a minimization. We're trying to minimize the number of parcels to set aside. Now, you could put a C sub J here if you wanted to minimize the cost, for instance. subject to the fact that for each species here, for each species belonging to the set I, remember I is a species, we need to find at least one parcel that would be able, that would contain that species, and that we would essentially set that parcel aside. And then here we are basically saying the parcels are either selected or are not selected. So it's a very, very simple formulation. Now let's look at an example that will illustrate this formulation. First on the blackboard, and then I will solve it in Cplex. I have now prepared an illustration to better understand the mechanism of the species set covering problem. The main idea here is that, as I mentioned, we do have a few parcels, right? We have 5 of them here that I've drawn in yellow. And for each of these parcels, someone has detected the presence of a specific species. So, example could be some bird watcher, and they are using the binoculars, and then they say, okay, I have spotted this particular bird or owl or whatever it is. Now, one caveat, it doesn't tell us the representation of that species within the parcel. Is there just one? Are there multiple times, multiple species of the same kind? We don't really know here. It's just a presence absence. So we have here species A, B, D here, E, F, and H. So we have a total of 5 different species spread out across 5 different parcels. So our objective is, which parcel should we keep in order to have all of the species represented? So as you remember, it's a minimization problem. We're trying to minimize the number of parcels that we need to set aside, subject to various constraints, but we are going to look at it from each species perspective. So species A here is represented in j equal 1 as well as j equal 2. So that's why you have x1 and x2, and it should be greater or equal to 1. So for sure, if we want to be, A must be represented, then either x1 or x2 will need to be open. For species B, it's represented here in j equal 1, and here, and in 4. So x1 plus x2 plus x4 greater than 1. For D, here, D appears in 2 and also in 3, so that's why you have x2 plus x3. E here appears in j equal 3 and j equal 4, that's why you have x3 plus x4. And H here only appears in j equal 5, which should be this one. Now it seems that I missed also F, so I'm going to quickly add this one afterwards. And then you of course have all of these different integer constraints. So let me now just add for F. F seems to appear only in 4, so we would have x4 greater or equal to 1, and this is for F. I had forgotten it, sorry about that. Okay, now we're going to see how we can solve this problem in Cplex. How many of these parcels do we need in order to preserve the system? Okay.
Okay, I will now show the solution in Cplex. So first thing here I have done to the left, you can see the notepad document with the LP file, which is the same as what we had in the blackboard. The minimization subject to constraint. You can see here how these two match, x1 plus x2, x1 plus x2 plus x4 greater than 1, x2 plus x3, x3 plus x4, x5, and x4 greater than 1. And then you have the binary constraints stating that every parcel is either selected or not selected. So if I'm good with this, go here, and then in Cplex I can do read. Then I'm going to carry that file right here, put LP. Okay, I'm going to optimize it. And so just want to see what the solution is 3. Okay, so that means that 3 parcels would be selected. That's how to interpret it. And now let's look at the solution here. Display solution variables all, and it tells us that x2, x4, and x5 are selected. So x2, x4, x5. Now let's look at the list of all of the species: A, B, D, E, F, and H. and there is nothing here that if I don't select 1 and 3 that does not appear in the other one. Okay, so that would essentially be the solution that we have.